Okay, hello everyone. I think we're ready to start. So, welcome to our Further Maths webinar. This is the third in our introduction to the Bridge the Gap series, and I'm Vishan Vora. I'll be taking you through this today. So, let's get started. Yep, so here's a quick session plan. We'll be talking a little bit about us, a little bit of housekeeping, and really this is just that we ask you keep your mics and videos off throughout the duration of this call, and then an introduction to matrices after that. So, a little bit about us. We are the Three Tutors. We're a relatively new tutoring company established in 2024. We're focused on personalized tuition and using adaptive teaching catered to your teaching style. So meet your tutors. We all have a strong academic track record across GCSEs, subject Olympiads, personal projects, and A-levels so far. We're all passionate about our subjects and giving the best tuition to you, and we all have all A-star predictions for all of our A-levels, and you can read more about us on the website. There's Reed, there's Samuel, and there's me, Vishan. So Bridge the Gap. This is aimed towards you if you're looking for a refresher, looking to dip your toes into uncharted material, or looking to deep dive straight into new content. We'll be doing this in small class sizes over the 6-week summer holiday and teaching you the first few months of A-level material. If you're interested, we encourage you to fill in the interest form. You can find this on this QR code, and it's also linked in our website. So really that's it for the presentation at the moment. We'll now be moving on to the Further Maths webinar. So let's have a look at learning objectives of the day. By the end of this session, we'll be able to define matrices, visualize matrix transformations, understand the different types of matrices, and I'll be teaching you a few of these, and then practice matrix operations. So let's get started. What are matrices? The matrices are defined as a rectangular array of numbers arranged in rows and columns. For example, might look like this. That would be a matrix. Matrices have practical applications in computer graphics, economics, and engineering. And here's a quick example. Spreadsheets are essentially one large matrix. And here's a quick tip. Each number or value is called an element. So for example, this number 2 would be an element. We refer to matrices usually using a letter. For example, the matrix A. And to refer to the elements, we refer to them in row column order. So this would be row 1. This would be row 2. This would be column 1. And this would be column 2. So when referring to the elements, for example, in matrix A, if it was a 2 by 2 matrix, i.e. 2 rows and 2 columns, this element would be lowercase a, row 1, column 1, so A11, and likewise with the others. This stays the same in a 3 by 3 matrix. For example, this one, this is in row 2 and column 3. But what does 2 by 2 or 3 by 3 actually mean? And those are your matrix dimensions. Again, it's rows and then columns. Visualizing matrix transformation. So matrices can be used to transform shapes and lines on graphs. I've got 2 examples here, one in 2D and one in 3D. In 2D, you can see this square over here has been transformed by a matrix to as this parallelogram. It can also be moved and rotated in these ways. The same applies in 3D, and the same can be done, as you can see on this graph here. There are a few different types of matrices, and they are on your screen now. Let's go through them. So a row matrix is a matrix that only has elements in a row, in one singular row. For example, this might look like this. As you can see, it only has one row, but 3 columns. As you might expect, a column matrix is the opposite. All of its elements will exist in one column, but multiple rows. For example, that. So rows 1, 2, and 3, but just column 1. We then have a square matrix, and as that might imply, a square matrix has the same number of rows as it does columns. For example, a 2 by 2 square matrix would have 4 elements, 2 rows, and 2 columns. Or a 3 by 3 would have 9 elements, three rows and three columns. A zero matrix, as it might imply, is a matrix that only has the element zero. It could have multiple elements that are zero too. For example, a 2 by 2 zero matrix. And finally, the identity matrix. I will show you what it looks like. It consists of ones and zeros. An example might be like that, but there's more on this later. Let's get straight into adding matrices. So in order to add matrices, there's a condition we must know. The matrices must have the same dimensions. This was mentioned previously. If you have forgotten what it means, here's a quick reminder. It is the number of rows multiplied by the number of columns. For example, in this instance, we've got a group of possible dimensions. Let's have a look at which ones we can add. So we're looking for a pair of matrices which would have the same dimensions. I can see that there's a 3 by 2 here and another 3 by 2 here. So that means two matrices with the dimensions 3 by 2 can be added together. Let's have a look at an example of adding these. So sticking with the 3 by 2, that means there's 3 rows and 2 columns. It would look something like this over here. For example, that might be 1, 2, 3, 4, 5, 6. Here's matrix A. We'll be adding it to matrix B. And in order to add these matrices, we'll be adding each element in turn. We'll be adding the element in the same position in each matrix. For example, considering we would end with a 3 by 2 matrix, we'll be adding the top left element of matrix A to the top left element of matrix B. So in this instance, we would get 8. So that's A11 plus B11. It goes the same for the next element, A12 plus B12, A21 plus B21, and so on. So in this instance, we would get 1 plus 7 is 8, 2 plus 8 is 10, 3 plus 9 is 12, 4 plus 10 is 14, 5 plus 11 is 16, and 6 plus 12 is 18. So that would be the result of this matrix addition. But what about subtracting matrices? It's very similar to addition. We still require the same dimensions. Here's a 2 by 4 example. Again, we would subtract each element in turn. So we would get a 2 by 4 matrix as our result. 1 take with 0 is 1. 2 take over 1 is 1. 0. Negative 3. You can have negative elements inside the matrix. So sticking with that, negative 4, negative 1, negative 2, and negative 1. That would be our answer in the 2 by 4 example. Here's a column matrix example for subtraction. Here we've got some algebra too, but this doesn't change anything. We would get a 4 by 1 matrix of 4 minus A, 3 minus B, 2 minus C, and 1 minus D. Now we're moving on to scalar multiplication. So scalar multiplication refers to enlargement. It can be about a fractional scale factor, which means the shape could get smaller too. It doesn't affect the shape created after in terms of translating it, rotating it, or reflecting it. It's just the area. For example, if we're multiplying the matrix 2024 by the scale factor 7, we would multiply each element by the scale factor 7 to get a 2 by 2 matrix as our result. So we would get 14, 0, 14, 28. As you can see, that is 7 multiplied by each element in that matrix. So this works for negatives, it works for fractions, and it works for algebra too. Let's have a quick look at a negative fraction as an example. For example, minus a half multiplied by, let's stick with the same matrix, 2024. We would get negative a half multiplied by 2, so negative 1, negative 1, 0, and negative 2. So as you can see, this is still an enlargement, although the shape has become smaller and technically reflected, it is still scalar multiplication. Now we're moving on to matrix multiplication, and this is one of the harder matrix operations, but we will be going through it nice and slowly. So I'll go through the conditions required for matrix multiplication later, but assuming that these elements can be multiplied together, as they're both 2 by 2 matrices, we know that this will result in a 2 by 2 output. And I'll confirm why that is later. So in order to multiply matrices together, we start by taking the top row of the first, so row 1 of the first matrix and column 1 of the second matrix. We multiply these together and we get the top left output. But why is that? And one way I like to visualize it is by crossing these over. So what we've done is we've taken the top row of matrix 1 and the left column of matrix 2. As you can see, these cross over at the top left element position, which suggests that they return the top left element. So in this instance, we would have AB multiplied by WY. But there's two elements on each side. So how do we multiply these? With matrices, we split them. So we start with A times W and add this to B times Y. So we get AW plus BY. So that is our answer to this top left element. I'll go through the rest of the matrix now a little bit faster. So for the top right element, we would be using the top row of the first matrix, but this time the right column of the right matrix. If we were to cross it over, you can see they align at the top right position. So that gives us this element here. In this case, you would get AX plus BZ. For the bottom left element, we would be multiplying CD by WY. We would get CW plus DY. And for the bottom right element, we'll be multiplying CD by XZ to get CX plus DZ. So that is how you multiply matrices. But as I mentioned, there are some conditions involved. For example, the number of the first matrix's columns, so that's the first matrix's columns, has to be the same as the number of the second matrix's rows. That might be a little bit difficult to wrap your head around at first. Let me break it down for you. Essentially, this means you take the dimensions of each matrix, so the rows by the columns, and you compare whether the number of columns is the same as the number of rows. So in this top instance, a 2 by 2 multiplied by a 2 by 2, it has the same number of columns as it does rows, and we get 2 by 2. That means that they can be multiplied together. It goes the same for the second example. Although the outer numbers are different, we still have the same number of columns in the first matrix as the number of rows in the second matrix, which suggests they can be multiplied together. Moving on to the third example, this has one column and 2 rows, which means they can't be multiplied together because those two middle numbers are different. And going on to the last one, we've got 2 3s in the middle, so we know they can be multiplied. Here's a little trick. What I like to do is lay out my dimensions. For example, let's take 4 by 5 and 5 by 2. And I like to draw a little circle around the middle two to double check if they're the same. Now that I know these are the same, I know they can be multiplied. But how do you know what it outputs? There's a 4, a 5, and a 2. But what are the dimensions of the output matrix? And the way to figure that out is by looking at the outer numbers. So as you can see in this example above, I've underlined the 7 and the 5. We know that since these matrices can be multiplied, the output would be a 7 by 5 matrix. So in this example, we would get a 4 by 2 matrix in the output. And again, during the Bridge the Gap course, we'll be going into why this is and how you can prove this. For now, let's look at some examples. So let's say we were to take a 1 by 2 matrix and a 2 by 3 matrix. I'm going to stick with the example AB. I'm going to change my 2 by 3 example to 3, 4, 5, 6, 7, 8. First of all, how do we check whether these matrices can be multiplied together? Again, using the circle trick, we know that these two middle numbers are the same, which suggests that they can be multiplied together. How do we determine what the output would be? We look at the outer numbers. So we know that the output of this matrix would be a 1 by 3. So we would get a 1 by 3 matrix in the output. Let's move on to multiplying them. Again, we start off with the top row, and in this case, it's the only row, which makes it easier for us. We multiply it by the left column. In this instance, we get 3a plus 6b. We then move on to the next element, and for me personally, I move on to the element on the right. So I know I would use the same row because in this case, it is still in the top column. This is the only, sorry, and still in the top row. This is the only row in this instance. So I'd still be using this row, but I'd be using the next column. And I know I'd get 4a plus 7b. For the next one, it would be AB multiplied by 5, 8. So I get 5a plus 8b. And then for the bottom row, I'll be using the same row in the left matrix because that's the only row I have. So I would get nothing, actually. This is our final answer. As expected, this was going to be a 1 by 3 matrix. Because that is our only row, that is the only row in the matrix we'll be getting in our output. We'll now be moving on to the identity matrix. So the identity matrix is a matrix that only consists of ones and zeros, and it's arranged so that the ones are diagonal. So in this 2 by 2 example you can see here, it only consists of ones and zeros, and the ones are diagonal. They always have to be in this format. In the 3 by 3 example here, there again are only ones and zeros, and the ones are in this diagonal line. The identity matrix is always denoted as the letter I. As you saw earlier, matrices can be referred to with letters, such as the matrix B, for example, or the matrix M. With the identity matrix, it's always referred to as I, or the matrix I. When applied as a geometric transformation, it has no overall effect. What this means is if you had a shape that was going to be transformed by the matrix I, there would be no overall change to this shape. It would have the same area, would be in the same position. For example, here's a shape with its coordinates laid out, and we'll be going into more depth about why shapes are labeled like this during the Bridge the Gap course. If we were to multiply the matrix 1, 0, 0, 1 by this 2 by 4 matrix representing coordinates, we would get the exact same matrix in our output. And let's check a quick element. Let's check this one. We know that it would be 1, 0, multiplied by 5, 6, to 1 times 5, plus 0 times 6. And I believe that gives us 5. So it does confirm that the identity matrix has no overall change on this shape's coordinates. Let's move on to matrix inverses. So the inverse of a matrix is a matrix such that when applied to a different matrix, it results in no overall change. So if you've got the matrix A and you're looking for an inverse of this matrix, it's denoted with a -1 in the superposition. So this doesn't mean a to the -1 because that would suggest 1 over a. That is incorrect. That is not the same thing. A to the -1 in this case, when referred to as a matrix, represents the inverse. What actually are inverses though? So when you've got a shape, what this means is once matrix A is applied to a shape, the inverse brings it back. to its original position. So in summary, today we've learned some addition and subtraction, and we know that the conditions for this are that they must have the same dimensions. And for multiplication, the first matrix's columns must be the same number as the second matrix's rows. So again, the dimensions are labeled as such, rows by columns. In this instance, we use the circle trick. We know that there's three columns in the first matrix and 3 rows in the second matrix. So we know they can be multiplied together, and we use the outer numbers to determine what the dimensions of the output matrix would be. We know that's 2 by 2. Let's have a go at some practice questions. So the first example is scalar multiplication. All we do is multiply the 2 by every element in the matrix. So in our output, we get 6, 2a, 8, 2b. Again, all I did was multiply this 2 by each element in this matrix. And then we have an example of addition. So for this one, because each matrix has the same dimensions, we know that these can be added, and it results in 10. Oops, sorry about that. 10, 12, 14, and 16. And in this final question, I just want you to have a think about what would the output be of a matrix multiplied by the same matrix to the -1. We know that this matrix represents the inverse of the previous matrix. And as we learned previously, this would return no change in the shape. We know of one other matrix that returns no change in the shape, and that's the identity matrix. So that is the end of our Further Maths webinar. Let's have a look at what our learning objectives were. We can now define matrices. We know that matrices are an array of rows and columns, and they contain elements. We can visualize matrix transformations. We know that when they are applied to a shape, they can cause reflection, enlargement, rotation, and translation. We know a few types of matrices. We visited row matrices, column matrices, identity matrices, and inverses. We also looked at zero matrices. And we practiced some matrix operations like addition, subtraction, scalar multiplication, and multiplication. So I'd like to thank you all for coming, for listening to me talk about Further Maths today. We'll be going into more depth about these topics during the Bridge the Gap course over this summer. If you do want to take part in this, do sign up on our website. And in the meantime, if you would like to contact us, please do email us at the3tutors@gmail.com or visit our website as linked there. This was the Further Maths webinar. We encourage you to stay in touch with us by following us on our social medias. And I'd like to thank you all for coming.